So after having some introduction to what vector-valued functions are, let's start doing calculus with vector-valued functions. And so the first thing we need to do, we think back to Calc 1. Well, what order do we do things? You think maybe we start with a derivative, but no. Before we do the derivative, we do continuity. And before we do continuity, we do limits. So we're going to start off by talking about limits of vector-valued functions. So right here is the very formal definition of what a limit of a vector value function is. So we're writing r of t is f of t I hat plus g of t j hat plus h of t times k hat. Let L be a vector. So we say that the limit as t goes to a particular value of t, like limit as t goes to 7 of r of t is equal to this particular vector r, L, like the vector would be 1, 2, 3, if for every epsilon greater than 0, there's delta greater than 0, such that for all t in the domain, the absolute value, which here absolute value is actually a magnitude, a length, RT minus L is less than epsilon, whenever the absolute value of t minus t naught is strictly between 0 and delta. And so this is the so-called epsilon delta definition. You may or may not have seen an epsilon delta definition for limits of just a one variable, a scalar value function in Calc 1. If you didn't, don't worry about it. I'm not expecting you to understand all of this to know what's going on. Essentially what this says here is that, like, you tell me how close you want to get to the target value, like the specific vector 1, 2, 3, and there's some, there is some, distance away from the t naught value that if you're within so much of that, you're guaranteed to be close enough to L. Again, this is a lot. I'm not going to test you on this formal definition here, because in practice, we can just reduce everything down to one-dimensional limits. So suppose that the limit as t goes to t naught of f of t is equal to some constant L1. The limit as t goes to t naught of g of t is some constant L2. Limit as t goes to t naught of h of t is some constant L3. Then the limit as t goes to t naught of f of t I hat plus g of t j hat plus h of t k hat is exactly what you'd expect. F of t goes to L1. So we have L1 I hat. G of t, the limit of that is L2. So then we have L2 j hat. And then h of t, the limit of that is L3. So we have L3 k hat. What's going on here? In order for the limit to exist, each one of the limits of the three underlying, component functions here, those limits all have to exist, and then the limit is exactly what you'd want it to be. So as a quick example, if r of t here is cosine t I hat plus sine t over t j hat minus e to the t k hat, limit as t goes to 0 of r of t will be, we just want to have, the three limits separately. It is the limit as t goes to 0 of cosine t, that times I hat, plus the limit as t goes to 0 of sine t over t, all of that times j hat, plus the limit as t goes to 0 of negative e to the t, all of that times k hat. And now we just have to compute these three limits separately. The limit as t goes to 0 cosine t, that's just plug in 0. That is 1. The limit as t goes to 0 sine t over t, that's 1 to know off the top of your head. That limit is also 1. So 1 times j hat. Limit as t goes to 0 of negative e to the t, that will be negative 1 just by plugging in. Negative 1 k hat. So the answer here is 1, 1, negative 1, written in this form. Okay, so limits. If you can do limits in Calc 1, you can do limits of vector-valued functions. Just take the limit of each component separately. Okay, what's going on here? The next thing we want to talk about has to do with continuity. What does it mean for a vector function to be continuous? It's if the limit of the vector value function is equal to the vector value function evaluated at the t0 value in question. Again, this is exactly the parallel definition to continuity that we should expect from Calculus 1. R of t is continuous if it is continuous at every point in its domain. So again, you can kind of go after this that, you know, we can do the same thing as before. If we write R of t is equal to f of t I hat plus g of t j hat plus h of t k hat, then R of t is continuous, CTS, abbreviation for continuous, if and only if all of f of t, g of t, h of t are. So if you can do continuity for functions in Calculus 1's continuous scalar value functions, you can do continuity of vector valued functions. Okay, moving our way through our tour of everything. Derivatives. So I'm going to kind of skip over all of this stuff and just say, look, this is exactly what we should expect it to have be. The vector function R of t of f of t I hat plus g of t j hat plus h of t k hat has a derivative at t if f of t, g of t, and h of t all have derivatives at t. How do we find the derivative? Well, r prime of t is, take the limit of the difference quotient, r of t plus delta t minus r of t divided by delta t. Take the limit of that as t goes to 0. And you can show, I'm not going to go through all of the derivations, take a look at the textbook if you want to see it. It just turns out that you end up with the derivatives of each underlying component here. So if you can do derivatives of scalar value functions, just do it 3 times, and you can do derivatives of vector functions. So if r of t is t squared times I hat plus e to the t j hat minus sine t k hat, r prime of t is, we just take the derivative of each part separately. 2ti hat plus e to the t j hat minus cosine t k hat. So again, if you can do derivatives of scalar value functions, you can do derivatives of vector functions.